Both exothermic processes, processes with delta H less than 0, and endothermic processes, those with delta H greater than 0, can be spontaneous. What this means is if we want a quantitative indicator of whether a process will be spontaneous or not, we have to look beyond enthalpy. Enthalpy cannot be the only factor that accounts for spontaneity. There's got to be something else in play here. Enthalpy has a lot to do with the energy of a chemical system, but the arrangement of this energy is just as important for spontaneity as the energy itself. So releasing energy is not the entire story. The arrangement of that energy and what happens when it's released or absorbed in terms of arrangement is also important. That's captured by a new state function called entropy. We use the letter S to abbreviate entropy, and for reasons that will become clear shortly, it has units of joules per Kelvin, or energy per temperature. Entropy is a measure of molecular randomness or disorder, but the broadest conceptual definition of entropy treats it as energy dispersal. So we just alluded to this idea that the arrangement of energy is very important for spontaneity, and one of the insights of the second law is that energy tends to become more spread out in spontaneous processes. So we can think about this, for example, for a gas inside a box. If we start out with the gas particles clustered in one corner of the box, the kinetic energy of those gas particles is relatively concentrated, that is, not dispersed. It's concentrated in one corner of the box. But if there's no barrier between the gas particles and the rest of the container, then over time we can probably intuitively imagine that the gas particles are just going to spread out spontaneously. And this spreading of the kinetic energy of the particles is exactly what we mean by energy dispersal. But the power of this energy dispersal concept is that it goes beyond just dispersion in physical space. It goes beyond just filling up a volume. We can also think about particles spreading over different quantum mechanical energy levels, for example. As you deepen your understanding of entropy in the second law, it's worth keeping in mind this definition of entropy as energy dispersal. It's a really nice conceptual definition that applies to a variety of situations and kind of subsumes many of these situations where you would treat entropy simply as disorder. Let's return briefly to this question of why entropy has units of joules per Kelvin. To understand this, I think it's most useful to think about delta S, the change in entropy, for example, when one system transfers energy or disperses energy, we might say, to another. The extent of the change in entropy when energy is transferred from one system to another depends on temperature. Say, for example, a certain amount of heat was transferred from system A to system B. Let's call that amount of heat Q. The amount of energy dispersed when heat is transferred from A to B depends on B's temperature. The greater the temperature for a fixed value of Q, the lower is delta S. And for the same value of Q, the lower the temperature in B, in system B, the greater the delta S. Why is this? Well, let's develop an intuitive analogy for this. Think about someone in a massive football stadium cheering on their favorite team. The energy they're dispersing in the form of that cheer is a drop in the bucket compared to the total thermal energy in that stadium, which is buzzing with thousands of people and tons of noise. It's just a very noisy situation. So the change in entropy in that case, due to that one cheer, quote unquote, is relatively small in the grand scheme of things. That one man cheering is just a drop in the bucket. Contrast that with that same level of cheering in something like a quiet symphony hall. In that situation, the overall thermal energy is much lower. Everyone's sitting in their seats, everyone's quiet, everyone's focused. The disruption caused by that one man shouting and cheering is going to be much larger in that case in the symphony hall. This helps us see that in a lower temperature situation, like our symphony hall, where particles are subdued and moving slowly, not vibrating very much, all that good stuff, a particular quantity of energy dispersed is going to correspond to a large delta S. On the other hand, in something like our soccer stadium, where the thermal energy, kind of the baseline energy, is much higher because everybody's clapping and cheering, that same quantity of cheering, that quantity of energy transferred, is going to correspond to a much lower delta S. To help deepen our appreciation for what entropy means, it can be helpful to predict qualitatively the sign of delta S for different phase transitions. And as a basis for all of these, keep in mind our prior picture of a concentrated gas spreading out spontaneously to form a gas that fills the entire volume of its container. The situation on the right is the high entropy situation, and the situation on the left is low entropy. So for this process, delta S is greater than 0, and for any sort of phase change that goes in this same direction of spreading out the particles and their kinetic energy, we should expect delta S greater than 0. So for example, in a solid, the molecules are very well ordered and relatively concentrated. Generally, solids have a greater density than corresponding liquid and gas phases, for example. When we melt the solid to form a liquid, we're spreading out the particles and dispersing their energy over a larger volume typically. So in that case, delta S, the entropy change, is greater than 0. And this is, let's call this a medium entropy situation if we label this as a low entropy situation. In evaporating and going from the liquid to the gas, we again are going from a relatively well-ordered situation, relatively concentrated energetic situation here, to a situation where now the particles are completely separated from one another and bouncing around the entire volume of their container. This is a very high entropy situation. And once again, in going from the liquid to the gas, we have delta S greater than 0. For the reverse situations, the opposite is true, which of course must be the case since entropy is a state function, right? If going in the forward direction amounts to delta S greater than 0, going in the reverse direction amounts to delta S less than 0. But we can also think about this intuitively, and really you should, in going from a gas in which the kinetic energy is dispersed over the entire volume of a container to a liquid where the substance has concentrated itself into a single, say, pool at the bottom of the vessel, we're decreasing the entropy of that substance. This same sort of idea can also be used to predict qualitatively the sign of delta S in chemical reactions, particularly those that change the number of gas molecules present. Introducing more gas molecules tends to increase entropy. A nice example of this effect in action is the decomposition of gaseous N2O4 to form two NO2 molecules, where all of these are gases. The N2O4 and the NO2 are both gases. In pushing this process forward, we've doubled the number of total gas molecules present, right, since each N2O4 molecule has split into two NO2 molecules. In increasing the number of gas particles, we've increased the entropy. And notice that as these molecules separate, as this bond between the two NO2 fragments breaks, we've dispersed the energy that used to be concentrated in this one N2O4 molecule over a larger volume, you might say. We could imagine that individually the NO2 molecules maybe have less energy than the N2O4 molecules, but that energy is spread over a larger volume and a larger number of particles, and that amounts to an increase in entropy, since we're dispersing energy. A similar idea applies to dissolution processes, which are also generally associated with delta S greater than 0, an increase in entropy. On the reactant side, we have solid sodium chloride and liquid water. This is a relatively well-ordered state in which the sodium chloride is concentrated into a relatively small volume. What happens during the dissolution process is water molecules start disrupting the well-ordered ionic bonds between the sodium cations and the chloride anions until we end up with the situation at the right, where each ion is surrounded by a group of water molecules. There are actually a couple of different effects in play here. On the one hand, the well-ordered sodium chloride crystal is broken up into ions, and the separation of these ions clearly amounts to delta S greater than 0. One way to think about it is that the energy that was concentrated in these ionic bonds is now dispersed over the entire solution. However, the water molecules have actually appeared to attain some degree of order, right? They're surrounding the ions and pointing in a particular direction, and that suggests actually that for the hydration process, for the process of the water molecules surrounding the ions, delta S is less than 0. Since the water molecules, which were relatively disordered in the liquid phase, are now in a structured arrangement around the ions. Put another way, the energy of hydrogen bonds between the water molecules, which was dispersed over the entire liquid phase, has been transferred or concentrated in a sense into these ion-dipole interactions of the water molecules with the ions. The net effect in this case, as it is for pretty much all aqueous dissolution situations that are spontaneous, is that delta S is greater than 0 overall, since the increase in entropy due to ion separation overwhelms the decrease in entropy due to hydration.